Hi, welcome to Math 408, L functions and sphere packing, lecture 16. I am having tremendous technical difficulties with all the different systems today, and it's not just my computers, it's also the computers in the previous room. It would not let me launch browsers, it would not let me send one of those days. So I want to get through this lecture as fast as possible so I can end this technological nightmare. So what I want to do today is talk a little bit more about interpolation. So it's been a while since we've done interpolation. And the goal is, given some values, when can you determine a function completely? Now, if you have some information about what the function looks like, the problem becomes a lot easier. If the function is polynomial of a fixed degree, okay, I know enough data points, and I know exactly what's going on. So I will start with the Bohr-Mollerup theorem. So most of the time you see Bohr mentioned in the physics class. This is his brother, who is a mathematician and has a really nice theorem. And we know the gamma function we define as the integral from 0 to infinity, e to the negative x, x to the s minus 1 dx, at least if the real part of s is greater than 0. And it has a continuation, so it satisfies a functional equation. Gamma of s plus 1 is s gamma of s. And so knowing that, we can find its value everywhere. So what they proved is the following wonderful result. Gamma is the unique function satisfying the following. And I'm not going to go into the proof of f of 1 equals 1. So this is a renormalization statement. The second one is f of x plus 1. Oops. X plus 1 is x, f of x, if x is greater than 0. And third is f is logarithmically convex. So if you take the logarithm, you get a convex function. So this is almost enough to uniquely specify the gamma function. Not quite. We need a little bit more. We need the log as convex. Do we really need f of 1 equals 1? Well, otherwise, if we just look at the functional equation, if I rescale the value of the function by 5, it's still going to be true. So the functional equation by itself can't be enough. You need some kind of normalization its value at 1 point. So 1 and 2 is not surprising. What is surprising, and I've been having my son do too many Geico jokes in front of me, what's surprising is that all you need to do is add 3, and you now uniquely determine the gamma function. And the reason is, again, we have this beautiful functional equation. When you look at it just at the integers, 1, 2, 3, 4. Well, what's annoying is, gamma of s plus 1 is s gamma of s, so this is the same as s factorial if integer. So 1 would just be 0 factorial, which is 1. 2 would be 1 as well. 3 would be 2 factorial, which would be 2. 4 would be 3 factorial, would be 6. And so on and so on, expanding very rapidly. If you want to draw a continuous, nice function through it, it seems reasonable that there should be 1. But the question is, why is there only 1? We're not just saying that this is true for integers. We're saying that this is true for any x. We have just one region where we know. All right. So I'm going to just write what we are going to be leading up to today. And I'm going to just jump ahead to the beautiful formula. And the goal is the following. F is nice. F hat is very nice. So just nice is not enough. Then of x is the sum, and it goes from minus infinity to infinity of f of n times the sine of pi x minus n divided by pi of x minus n. And here I want the support of f hat to live in minus and half. So have you seen support in any of your other classes? Okay, so what does it mean for the support to live between minus and half and minus and half? So f hat is 0 outside. What are we talking about? Sum minus infinity to minus f of n times this fraction. Yes. Does this formula look interesting to you? It does look a lot like a Dirichlet kernel. Are you surprised? There's actually. Are you surprised? This looks like the Dirichlet kernel. Well, I'm talking about f and f. So maybe it's not so surprising that Dirichlet is coming at some point. There's something I think remarkable about this formula, though. So it's not showing up over here, which is an interesting. And in fact, I don't know if you noticed, I can always check the video footage really quickly. When I wrote it, I checked my notes again. There's no hat. But of course we know sums of x and sums of f integers are related to summation. So while initially I might consider the typo, I spent the time before class not looking at my notes, regarding sound issues. But what else is surprising? You've given two great answers already. And remember, when you make comments, please send me emails. Doesn't have to be during class. But there's something else I find very surprising about this formula. We start off with the gamma function. What information do you need to know? We need to know its values everywhere. And essentially, if we assume our function has these three properties, if we know the gamma equals 0, 1, 2, we know it everywhere. So it's periodic. So if I increase x, I'm definitely going to be periodic. It's periodic. Am I? Because I don't have a sign down below. So but I think there's something remarkable about this. What information determine an arbitrary point? Yeah. Just need f of n to find f of x. If I'm looking over, there's lots of different functions that goes through these values of the integers. And so what I'm telling you is that somehow, if f and f is sufficiently nice, knowing f just at the integer is enough to allow you to interpolate it everywhere. I have to know it at all the integers, that's a lot. But it's remarkable that its values of the integers. You keep seeing complex analysis, the analysis results with spirits to that. It would be wonderful if that course was a prerequisite. It's also just a beautiful class. It's worth taking at some point. I could have, but in the theory is that you would lose students. And so to some extent, you can only do electric analysis just on some of the things we need. When do you have beautiful statements, just knowing it as some allows you to get it everywhere else. Now the first question is, here's ice function f of x. Here's hat of y integral to minus infinity to infinity f of x e to the negative tiny I x y dx. It turns out f double half x of x is f of negative x. So the Fourier transform is almost the original function. It is for which types of functions. Even. So f is not a big deal. It's not a big deal. If f is not even, what do you do? No. So taking it twice gets you back to f at negative x. Yeah, take it 4 times. So if you take the Fourier transform, you'll always return to where you start. If you take it twice, if you're even, you return to where you start. You could try to prove some of these inversion formulas. You know, f of x is the integral to minus infinity to infinity of f hat of y between e to the 2 x y dy. So Fourier inversion. And it's true if f is in the Schwartz space. So this means in the Schwartz space. I think Schwartz has a T here. Schwartz space. So it means that x plus 1 to the n take the derivative, the absolute value, this will go to 0 as the absolute value of x goes to infinity. So what this means is take whatever derivative you want, however many derivatives you want, multiply by however high of a polynomial you want, and it's going to go to 0. So another way of saying it is all the derivatives go to 0 faster than any polynomial. Why do you think I'm writing absolute value of x plus 1? I'm just being extra safe and extra cautious. When x is large, absolute value of x plus 1, that's less than 2x. Or it's greater than 1/2 x. This just helps me so that as x goes to 0, everything is still going to be. I'm not going to have maybe a 0 here. It's not really a usually you don't even put in the plus 1, you just do the absolute value of x to the n. I just always am worried about eventually have I multiplied by 0 something that's vacuous. But as long as my function is differentiable, if I just look at the interval minus 1 to 1, it can't be that bad for any derivative. And so I really don't need this, and I could just look at the absolute value of x to the n. Let me guess next. Absolute value. So this is a function whose derivatives all decay as fast as you need, as long as you only need things to have polynomial decay. Does not mean you have exponential decay. I could give you maybe the function e to the square root or absolute value of x. If I give you that, that's not going to be growing exponentially. So if I looked at 1 over that, it would not be decaying exponentially. But it would be decaying faster than any polynomial. Are there any Schwartz functions? Give me a Schwartz function. Gaussian. So f of x equals e to the negative x squared will be in the Schwartz space. And for a lot of things, Gaussian is enough. We could try to prove the Fourier inversion formula. What's your first thought about how you might try to prove this? So we're integrating f hat e 2 pi I x y. Yeah, double integral. So we could say, let's consider the integral from minus infinity to infinity, the integral from minus infinity to infinity f hat of y, I'll use t as the dummy variable, will be f of t, e to the negative 2 pi I ty, e to the 2 pi I xy, so it should be e to the 2 pi I x minus t y dt dy. What would you like to do? And so this is y goes from minus infinity to infinity, and this is t goes from minus infinity to infinity. I don't care if you can do it, but what would you like to do? You've got a double integral. I'm sorry? So one is to try to separate them, or swap them. And so either one is a good thing to try. Let's do the y integration first. Well, okay, then separating them, let's switch the orders of integration. The problem is if I put in absolute values, this is of absolute value 1, and when I do the y integration, it's terrible. So we're not going to be able to just naively go through this. But if you think about what's going on, what happens if x does not equal t? Well, then if I do the y integration, I'm going to just keep going through full periods of sines and cosines. So you might think, well, if I just take x not equal to t, I'm going to just have a tremendous amount of cancellation. I'm going to just keep getting full cycles. I have to worry a little bit about things at infinity, but maybe there's no real contribution, and when x equals t, then I have something that's identically 1. And you would almost have like a Dirac delta function would come in that would then just pull out the value of f of x. This is a really hand-wavy argument to just give you some sense of why it might be true. We could spend the entire course proving results in Fourier analysis. We will just assume that there is this relationship between a function and its Fourier transform. Now, one of the things I wanted is, in our statement, we need f hat to be very nice. We need it to be what's called band limited. It needs to live between minus a half and a half. So find f such that f hat has support in minus a half a half. Let me check the chats. So the question in the chat is, f is determined by its behavior at integers, Cauchy's integral form. So this is similar to stuff like when in complex analysis you often have a holomorphic function is determined by its values on the boundary. There is a whole branch of mathematics dealing with problems like this. How can we find a function f that has support in such that f hat has support in minus a half a half? Any thoughts? I want a function f, but when you compute the Fourier transform, I want the support to be in minus a half a half. What can you do? I have a feeling you will call my answer cheating.
You get like odd somehow?
But I need you to give me a function such that its Fourier transform lives in minus a half a half.
0?
Oh wait, this is the COVID era. The chuck must remain 6 feet away from you. So I think that's the best I can do in the COVID era. Yes, we could take f to be identically 0. Can we find any other functions? But in many instances, the wise-ass answer of 0 is not a bad start. To at least have there's something in the space. So here's the x-axis, and here, here's our function f, function f hat. So much of math is about changing your perspective. Let's see, do I have coins? How many of you have done measure theory? Have you seen the coin analysis of measure theory? How to explain the big integration through coins?
No.
Okay.
Maybe.
So this is not going to be that impressive. I went to the bank recently and I deposited all my small coins. I have a dime, a penny, and a nickel. It's not that hard to figure out how much a dime plus a penny plus a nickel is. But imagine I give you the following: penny, nickel, nickel, penny, dime, quarter, quarter, nickel, quarter, penny, penny, quarter, quarter, nickel, quarter, penny, penny, dime, half dollar. And on a high note. Can somebody give me one way to figure out how much money we have? Add it. 1 plus 5 plus 5 plus 1 plus 10 plus... So if you add, that's Riemann integration. And you're walking along the x-axis. What's the other way to figure out how much money you have?
Count the quarters.
Right. Number of pennies plus 5 times the number of nickels plus 10 times the number of dimes plus 25 times the number of quarters plus 50 times the number of half dollars. That's Lebesgue integration. Where instead of looking at things over here, if I give you a function, instead of calculating things like this, which is Riemann, for Lebesgue, what we do is we break things up based on the y values. So if I want something in this band, it corresponds to something down here plus something down here. It's another way of doing the integration. So rather than focusing on the domain, I focus on the range. And then for different parts of the range, I say, well, which part of the domain does that correspond to? What's the measure of that? How many of them if I have coins? How many nickels? How many dimes? Over here, I want you to find an f such that f hat is nice. If you look at it the right way, it's trivial. How should we look at this? Because we have to show that at least one function exists, or this formula is going to be useless. So how can you make sure that you start off with a function f such that f hat is nice? That f hat lives between minus a half a half?
Could you just choose an f hat that's nice?
Yes! Start over here with an f hat that's nice. And then go backwards. Use the Fourier inversion. So if we start off with a nice f hat and pull back, then we'll have a nice f. So this at least proves that such an f exists. Okay. Just check the chat. So there's a couple of nice results. The first is if f is in the Schwartz space, then f hat is in the Schwartz space. That's good. So if you start off with a really nice function, its Fourier transform is really nice. So it's worth collecting a couple of facts about Fourier transforms. So f of f hat of y is equal to minus infinity to infinity f of x e to the negative 2 pi I xy dx. Now, to talk about the Schwartz space, we need to know something about how fast a function and its derivatives are decaying. So let's say we want to take the derivative of f hat. would you take the derivative of f hat? How could we do that?
Polynomial brackets, maybe?
Okay, which would be, what would we do?
Would it just be this times negative 2 pi x?
So what did you do to get that?
Oh, shit. Partial derivative of the...
But you have to say something. You have to justify what you're doing, or this becomes a physics class. What do you want to do to take the derivative? I'll write it slowly. It's d by dy of the integral from minus infinity to infinity of f of x e to the negative 2 pi I xy dx. You want to switch them. And you want to say this is the same as the integral from minus infinity to infinity of f of x. And now you want the derivative to come in here and hit that. And that's going to give you negative 2 pi I x, right? Because I'm taking the derivative with respect to y. E to the negative 2 pi I xy dx. Uh-oh, will this integral converge? Because I've now multiplied f by something of size x. Do we know that it's still going to converge y?
Schwartz.
Yeah, f is Schwartz. F decays faster than any polynomial in x. So no matter how many times I differentiate, no matter what power of x I have here, f is going to have enough decay that this will exist. So all of these derivatives will exist. And what it tells you is the derivative of the Fourier transform is the Fourier transform of the function times negative 2 pi I xy. Basically, the Fourier transform converts multiplying by x to differentiating. Okay. So we just showed that if you multiply our function by x, its Fourier transform is the derivative of the original Fourier transform. So what we could do now is, instead of multiplying, we could look at the Fourier transform of the derivative. So let's look at the integral from minus infinity to infinity of f prime of x e to the negative 2 pi I xy dx. So I want to see, what is the Fourier transform of the derivative? How should we figure this out? How should we analyze this?
You could do it by parts.
Yes! So what do you want u to be?
E.
Okay, so what's u?
E to the negative 2 pi.
E to the negative 2 pi I xy. dv is f prime of x dx. Which is a very logical thing to try because we want to get back to the original function. So if we take dv to be f prime, when we integrate by parts, we'll just get an f of x. Now, when we take the derivative of u, what are we taking the derivative with respect to? What variable? X. So we get negative 2 pi I y e to the negative 2 pi I xy dx. So this will be uv minus the integral of v du. Do I have to worry about the boundary term uv? No. U is of size 1 in absolute value. V, f is Schwartz, so it's decaying rapidly. So the boundary term is just 0. So we get that our integral, the negative sign is going to reinforce that negative sign. We can bring the 2 pi I y outside, and we'll get the integral from minus infinity to infinity of f of x e to the negative 2 pi I xy dx integral. It's just f hat of x. And this is going to be f hat of y. F hat of y. And this is just going to be the Fourier transform of the function f prime evaluated at y. So we see the Fourier transform of the derivative has a really nice relation to the Fourier transform of the function. And we see this interplay between differentiation and multiplication. I'll risk asking, how many of you have taken a class in differential equations? Oh, excellent. 2 people? Have you seen the Fourier transform or the Laplace transform used to solve differential equations? Okay, so 1 yes, 1 no. I'm hoping you did not take the same class at the same time. Okay. I won't ask who was teaching, but there's a lot of things you can cover in differential equations. If you take a class, you learn very quickly it's hard to solve differential equations. It's much easier to solve polynomial equations. One of the great applications of the Fourier transform is if you take the Fourier transform of a derivative, it's now just a polynomial times the Fourier transform. So when you have a bunch of different derivatives, you end up getting polynomial equations. And then you will have to do like an inverse Fourier transform of a polynomial times a function. But the idea is that you can actually use this approach to solve a bunch of differential equations. Okay, any questions so far? There's one more identity I need. And it's one I want. Okay. I want f sub t of x, I'm going to define to be f of x times e to the negative 2 pi I tx. So the question is always going to be, how is f hat of f of t related to f hat? Well, let's compute it. F hat of the function ft of x, so now evaluated at y, is the integral from minus infinity to infinity of ft of x e to the negative 2 pi I xy dx. So it should be clear what we do. We substitute for what ft is, and we will get the integral from minus infinity to infinity of f of x, and then we have a e to the negative 2 pi I tx. We have an e to the negative 2 pi, so it's e to the negative 2 pi I x plus t, no, y plus t times x dx. Right? Because this has a negative 2 pi I xy, this has a negative 2 pi I tx. They both have an x, so it's y plus t times x. Can you calculate this integral for me in terms of f hat?
F hat of y plus t.
It's just f hat of y plus t. Because the Fourier transform is just e to the negative 2 pi I, place where I evaluate the Fourier transform times x. So what this is telling us is that if we translate the Fourier transform, that is the same as multiplying our original function by a factor of e to the negative 2 pi I tx. Okay. So we're getting closer to our formula. So homework. Number 1, prove f in Schwartz implies f hashes in Schwartz. Number 2, find a f in Schwartz such that f hat is very nice. So support of f hat lives in minus a half a hat.
Can we still do 0?
I'm sorry?
Can I still do 0 for that?
Find 2. So the first one is worth 1 point, the second one is worth 9 points. We do not yet know that there is an affirmative answer to 2. What makes you believe that there probably is an affirmative answer to 2?
Construct f hat arbitrarily, and then inverse Fourier transform.
But it has to be Schwartz.
Yeah, so one of those will hopefully be Schwartz.
So you have to find something that's Schwartz. Do you think that such a function exists? Why?
You asked us to find one.
Well, the best or the most evil question, depending on your point of view, that I ever did in my career was when I was teaching abstract algebra at Brown. How many of you have taken a class in abstract algebra? Okay, I have not. I've taught it twice, but I've never taken it. So if you haven't taken it, there's something called a ring, and if a ring has an additional property, it's an integral ring. So part A was worth 5 points. It was, is the following set a ring? And part B worth 15 points, was it an integral ring? So 2/3 of the class wrote, oh, it must be a ring, else why would you ask part B for 15 points? It was not a ring, it failed closure. The one property that most people just don't even bother checking. Now, if you assume that it's closure and just manipulate, it actually was an integral ring. Given that I'm asking this question and I still have this beautiful result on the board, it is quite likely that such a function exists. You only need to find one such function. And so the question is, can you find a function where this is true? And then what's going to happen in sphere packing is my colleague who is the point behind all of this, the other Steve Miller, well actually I guess I'm the other Steve Miller, he got his PhD first. He was working with Henry Cohn and they were looking at trying to find functions that had certain properties and values at certain points, and if they could do that, they could then come up with better packings. And for all of these things, you have to prove that such a function exists. And frequently, that's the hard part. Sometimes it's nice to be able to give an explicit construction of it. Not only does it exist, hey, here's the one that works. I will accept existence first. One of the best ways to prove the existence of something is to physically say, look at this. And so that's one way to do it. So if you can give me an explicit function that works, it's not so bad. All right.
Does it go the other way? I'm sorry, for
Sure, no.
part 1. Is that, we talked about it earlier, but is that if and only if?
So you tell me. What is true about the Fourier transform of the Fourier transform?
Even, negative.
Yeah, it's basically just the function with flipping x to negative x. So if you want, it goes both ways. Absolutely. So the Fourier transform maps the Schwartz space to the Schwartz space. Another way of doing it is, that if you do the Fourier transform 4 times, you return to where you start. And so if I start off with a function that's Schwartz, if every time I take the Fourier transform I end up back in the Schwartz space, if I start with f hat and do 3 more, I'll return here. Okay, so we need to be able to show decay. We need to be able to show that we can construct such functions. And we've got 5 minutes left. I don't want to do the whole proof. I will mention maybe just one thing that we're going to want. And I'll end with this. We will use the sum, n goes from minus infinity to infinity, of f hat of n plus t is equal to the sum, n goes from minus infinity to infinity, of f of n e to the negative 2 pi I n t. And I am hoping now that we have not erased everything that I need. Good. Looking on the right board, the right side of the board, this is just f sub t of n. Right? And this is just f sub t hat of n. So why is this statement true?
Poisson summation.
Poisson summation. So this was the reason why we've spent so much time proving Poisson summation. And to do that, we had to develop a good amount of Fourier analysis. It's worth doing that because Fourier analysis is just so beautiful and so useful for so many problems. But here's where we're going to start to use it. And then we want to start analyzing things. Now let's assume the absolute value of t is less than a half. Which sum do you think is easier to evaluate, the left-hand side or the right-hand side? And then we'll call it a day after this, and I will yell at my computer. Although I guess I could record the yelling, but I won't be able to hear it if I play it back. Which do you think is easier to evaluate? And remember, f is Schwartz, f hat is very nice. So support of f hat lives in minus a half a half.
So the left side is only the central term will contribute.
Yeah. So what does the left-hand side equal?
F hat of t.
Just equals f hat of t. And now you can see why we like this formula. Rather than having to deal with an infinite sum, we now have just one term. We have an explicit formula for f hat of t. And the way the proof would continue is now we would take f hat of t, and if we just undo the Fourier transform, that should give us f of x. So I've had too many days where I've gone over by a few minutes, so to balance that out, today will end a few minutes early. Any questions on what we've done up till now?